Hey, it's Mr. K doing a video for AP Physics 2 tonight, and we are looking at some fluids, a little bit of buoyancy, a little bit of pressure. And start off, let's go ahead and talk about what pressure is. And pressure is equal to a force that has been distributed over some area. And if we look at the units of pressure, pressure is going to be force is newtons, area is going to be standard meters times meters, so meters squared. And we're also going to call this the Pascal, the PA. So if you ever hear us talking about pascals, and we're talking about pressure. And what we're going to do is we're going to look at how you can have pressure based upon the fluid or the thing that's on top of you. So let's take, for instance, this container. Let's say this is a container, and it's a container of height, I don't know, height L1. It's going to have a base of L2 by L3. And so if we were to consider this container was being filled up with water, if I were to fill this container up with water to maybe right here, then purple water, then this bottom would feel more and more and more force. But if that force was distributed over this big area, it wouldn't be that bad. So it's kind of like, you know, how does a knife cut you is one question you can ask yourself. Well, it cuts you by having this force over a very, very, very tiny area, and so that pressure is very high, so it can actually separate the skin cells. But with this thing, say we filled the whole thing up with some fluid, let's just call it water, and what would happen to the bottom here based upon it being filled up with water? And so we need to consider how much water we have. And so to consider how much water we have, usually what we do is we take the density of water. Density is going to be this rho symbol here, and that is going to be the mass ratio divided by the volume. And so if we were to just move this volume over, we would have this density again times the volume, and that should be equal to our mass. And usually we would then take our mass and multiply by g. So we're going to multiply both sides by g, and that's going to be our force. And so if we take this, I'm going to rewrite it like this rho of water times the volume of water times g, so essentially m times g, and we divide that by some area A, then we should get this pressure P at the bottom. All right, and that's just based upon how much stuff is in there. Now, if we were to really look at what these volume and areas are, we could say, hey, H2O is H2O, but volume is going to be L1 times L2 times L3, right? So we've got this this rectangular prism here, multiplied by G, and we're going to divide this by the area. The area of the bottom, is what we're talking about, would be L2 times L3. So what we figured out just now is that L2 doesn't matter, L3 doesn't matter. All that matters is the height, right? So the bottom area doesn't matter. All that matters is the height of this thing. So the deeper you are under a fluid, the more pressure you're going to feel. All right, and then based upon the area, that's going to determine the force that the area feels. So yeah, let's say you're in this submarine and it dives way, way, way down in the ocean. You want really, really small windows such that those windows don't take a whole lot of force. It's still going to be a huge amount of force, but the bigger the window you have, the more force you're going to have, probably exponentially, because it's going to be pi r squared. So be careful with that. So an equation that we need to consider here, a very important equation, is the equation due to depth of fluid, which is going to be pressure due to depth of fluid, which is going to be the density of the fluid times the height that you are in the fluid, and times g. All right. So how deep are you in that fluid? So that's going to be the height there. You might do a delta h if you want to. So rho gh or rho hg. We're going to switch it over to this side, and let's talk about lost my word there. Buoyancy, floating. So most of you have probably jumped into a pool. If you haven't, go ahead and give it a shot. If you drown, not my fault. Use buoyancy. So let's talk about buoyancy. If you put something in water, it feels lighter. All right, some things float, some things sink, but no matter what it is, it's going to feel lighter in the water. And the reason why is because of this thing called buoyancy. It's this force of the water trying to get back to where it was. So if you put something in the water, you push the water away. That water wants to go back to where it was because water is a fluid. It wants to fill the container that it's in, particularly the bottom part, right? So if you have this let's say this cube of side L1 and the bottom of, again, L2 and L3. These could be all the same, they could all be different, but we'll use them nonetheless. If you place this in water, then due to what we just figured out over here, every single side is going to feel some pressure. Now the top is going to feel some pressure going that way. That pressure is going to be over this area, so there would be a force downwards on the top due to the rho g h of however deep we are in this water. The bottom is going to feel some force, or the force from that pressure up that way, and so that would be some rho g h from the bottom. But the h down here is going to be h plus L1 because we are deeper, and we'll multiply both of these by the area, which is going to be the L2 and L3. L2 and L3. Okay, so that's the top and bottom. Those are the forces in the top and bottom. If you notice, the bottom has a bit more force than the top due to it being a bit deeper. Now the sides, as you are going down on the sides, that force is going to get bigger and bigger and bigger because you are also getting deeper and deeper and deeper. But the sides really don't matter because if you notice, let's just pick a spot right there. If that water is pushing in on the right side, it would also be pushing on the left side, and it would be pushing in the front, it would be pushing in the back. And if you're like me right now, I just saw this cube kind of like, this is this is the front, and then all of a sudden it was the back of the cube. It was really weird. But anyway, the sides don't matter, they all cancel out. So essentially what we're looking at is, once again, this. We are looking at the force on the bottom and the force on the top. I'm going to call the force on the bottom positive, and so I'm going to say that force on the bottom is rho. Which rho is this? This is the density of the water times g times h, which was the depth. I don't know what depth we are, but it's whatever depth, plus L1. This is the height of this cube or the height of this rectangular prism, whatever it might be. I'll call it L1, and that's multiplied by L2 and L3. We're going to subtract the force pointing downward on this thing, and that's due to the water that's on top of this whole thing, rho g h, and that's multiplied by L2 and L3 as well. So that being the case, if we were to distribute, let's see what we get. By the way, this is the sum of all forces on this object at the moment due to the pressure. There's also going to be the force of gravity on this thing, but I'm just going to consider these two, so don't mind me just yet. So H2O, G times H, right there. And I'm going to multiply by L2 and L3. And that is added to this rho H2O times G times, not H, but L1. L2 and L3 all distributed nicely, minus rho, I'm going to run into my other thing, G, H, L2 and L3, oh dang it, alright. So, real quick, this is just the forces of the water on here. I know I need to include the force of gravity on this actual cube itself, but I'm just going to worry about these right now. If you look, I've got a negative something, and that negative something is rho g h L2 L3. And over here, I've got rho g h L2 L3 positive. So those things happen to cancel out. So it doesn't matter how deep you are in the water. What it does matter is the dimensions of the thing you're placing in the water. So turns out that this equation, L1 times L2 times L3, happens to be the volume. So this is equal to, well, is this a force or is this pressure? Now let's not forget. So let's just go back. This is density, right? Density is going to be mass divided by volume. And if I multiply density by volume, I should get mass. So this is just mg. So that's a force. And this is the force, and it's pointing upward, of the buoyancy. Buoyancy. It's Buoy, I think. So this is the force of buoyancy on this object. And if you notice, you just find the volume of whatever the object is, and that is basically the fluid that you've displaced, the volume of fluid you've displaced. That weight of that fluid would be your force of buoyancy. So if you were to jump into a pool of water, your body's volume, that weight of water that's equal to your body's volume, would be the force of buoyancy on your body. If you were to jump into a pool of mercury, like metal, you would float really, really well because mercury is really dense. All right, so this density thing would be a lot higher. But any object inside of a fluid will have a force of buoyancy. Okay, because that fluid wants to get back to where it was. You pushed it out of the way, it wants back in, and so that is why you have this force of buoyancy on you. Now, for the last part, we're going to look at what happens if we float. And so, if we are more dense than water, you sink. If you're less dense than water, you float. In this case, we were acting as if this whole thing was submerged in water, as if it was more dense, or you pushed it underwater. And so let's run the conditions of, hey, maybe we actually float. And if we float, then what we need to do is we need to consider this thing. This thing has some density to it as well. It's got some volume to it, it's got some density to it, but let's consider that. So if we had this object and it were, let's say, floating somewhere like there, like that, then some portion of it would be, wow, I just skipped squares. But some portion of it would be above the water, right? So if you're floating, then your free body diagram should look like this. It should be a dot. You know that you have definitely some forced gravity on you, so the density of the block, just to be consistent with this stuff, times the volume of the block times g. That would be the force of gravity on you. And there'd be an equal force of buoyancy pointing up, right? And that force of buoyancy would be this guy, based upon however much volume of water you displaced. And so that force of buoyancy, again, this would be the mg, and this force of buoyancy would be the density of the fluid that you're in this case water, times g times the volume of the, can I fit it? Yeah, maybe, of the fluid displaced. Okay, so these volumes are not the same. But if we just simplified and made it a block, a part of that volume would be the same, and you're going to see here in a second. Let's just move these down here. So these need to be equal and opposite. And so they're not the Newton's third law equal and opposite, but they need to be equal and opposite in direction in order to cancel out here. So let's just take the rho H2O G volume displaced and set that equal to the rho block volume of block times G. I hate how these are in different spots, but we'll deal. G apparently cancel out. And then I'm going to do one more thing. This volume displaced. If we look at this cube here and just talk about that cube, the volume displaced and the volume of the block is going to be L1 times L2 times L3, whereas the volume displaced would be, well, the base of it, L2 times L3 times whatever this part is that's actually under the water. So I'm going to call that H. I'm just going to call this thing here H. And we're going to multiply by L2 and L3 to get that volume displaced. If you notice then, L2 and L3 cancel out, right? So that's interesting that all this stuff starts to cancel out. So we have the density of water, H2O, times the, let's call that, I don't want to call it H anymore, let's just call that L under. Yeah, that's L under. And so L under, Lunder. And that's equal to the density of the block times the L1, the actual height of the block. And that's kind of cool. And the reason why I'm going to say that's cool is because let's just move this over. Let's move the H2O density over here. Let's move the L1 over here. So if we have L under divided by L1, the height of the block, that's equal to the density of the block divided by the density of water. And that's kind of neat. I know I kind of went off the page, but that's kind of neat. And the reason why that's neat is this. If we were to say, all right, the density of water, let's just kind of run a little practicing here. The density of water is 1,000 kilograms per meter cubed. All right, standard density of water. If we say the density of the block is like 800, all right, then that tells me that that's going to be 0.8, right? Cancel, 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 cancel. 8 divided by 10, that's 0.8. Now, what does that mean? That means that 80% of this thing, as far as the height goes, is under the water, right? Because if I call it L1 like 1 meter, that means that this has to be 0.8 on top. All right, and that's actually really, really neat. So the stuff that's under the water, L under, that's 80% of it. And so there's a saying that says, you know, hey, if you see an iceberg, it's the tip of the iceberg, right? How much is actually under the water? And they say like 90% of it's under the water. Well, it turns out when you run this ratio, yeah, you get like 90% is under the water, and so about 10% would be above it. Okay, so I'm gonna end it here. It's kind of a long video already, but most of the derivation was done a little while ago, and I will stop there because now Peebs is putting more toys on my chair saying, hey, stupid, come play with me. All right, good night.